Hi everyone, and welcome to episode number 7 of CS350 Online. And I'm your host, as always, Leslie Eisted. So on today's episode, we're going to review semaphores and condition variables, which we introduced in episode 6. And then we're going to look at some other sources of race conditions, which we have been neglecting for the last few episodes. And we'll get an opportunity today to discuss deadlocks, which are one of the interesting consequences that can arise if you improperly use synchronization primitives. But first, it's time for our daily segment, the OS of the day. Today's OS of the day is one that is particularly important. It's called Multics. And Multics was released around 1969, and some of the computers that it ran on were primarily the GE645 and a Honeywell 6180. This operating system was a product of MIT, and the name Multics actually stands for Multiplexed Information and Computing Service. Not a bad name, actually. And we actually have a nifty little logo down here, which has a bit of meaning to it, which is kind of cool. Now, this is a first OS to do many, many interesting things. For example, it offered a single level storage. There was no separation between the file space and the address space. So you could access address spaces as if they were a part of the file system. And as you can imagine, that had some particular conveniences to it. They also supported things like dynamic linking, so processes could access data, include code from outside of their own address space, which is something that we do all the time and we kind of take it for granted. But you have to imagine that 40, 50 years ago, you couldn't take that for granted. Now, here's a particularly unique thing that Multics offered, and it was the ability to, while the system was actually running, you could reconfigure the hardware. So if you had 2 CPUs, maybe you would be able to actually remove one of the CPUs. Now you might be thinking, oh, do I reach my hand into a small computer and do I actually take out the other CPU? No, I mean like you would be disconnecting and wheeling a fridge across the room, a big thing. Or you could move tape drives around and add tape drives and remove tape drives while the operating system was running without having to restart. Now, this is actually the beginning of something which you use all the time, which is the ability to do plug and play. So if I have something like my little Wacom here and I plug it in, it just starts working. I don't have to reboot the OS. But I can tell you that in my experiences over the last many, many years, plug and play didn't always work. And in fact, in things like Windows 3.1, if you were to plug in even a new mouse, there is a really good chance that you actually had to reboot the operating system and wait for Windows or even install the driver and then reboot the operating system. Same with keyboards and a variety of other things. But today you can pretty much just turn these devices on, unplug them in, and they just work, and you don't have to think about it too much. Like my printer that's sitting underneath the computer over there, I've never installed a driver for it, not once. And anytime I need to print up, a little math sheet for my daughter so that she can, do school in the absence of school, I just plug it into my computer and it just works, and I don't have to do anything. But Multics kind of started that, which is kind of cool. Now, another thing that they realized is that maybe we should have a little bit of security. Now, it wasn't security in the sense that we have today, because in 1969, they didn't really have the kind of internet that we have today. And if you're looking at 69, the late 60s, early 70s, you're looking at the very early stages of the internet where everybody was really a trusted source. There weren't malicious individuals out there on what networks existed, so security wasn't a huge deal. But at the same time, they wanted to make sure that administrator privileges were very different from user privileges. You don't want a user to be able to come in and boot off fellow user programs. So they designed Multics with rings for security. So the inner ring, it's kind of like this diagram here, this inner ring is kind of like the kernel. And then as you go out and out, you get less and less privileges. And obviously security like that has not just increased over the years, but it has certainly evolved. And they had many, many, many other interesting things introduced in Multics. All right, so Why might you have heard of Multics? And by the way, you can probably find a web browser to emulate Multics and run it. The reason why you might have heard of Multics is because Multics is Unix's predecessor. And furthermore, many of the individuals who were responsible for implementing Multics moved on to Bell Labs to implement Unix. All right. So what happened on last day's episode? So on last episode, we introduced semaphores, which, if you remember, a semaphore is a kind of synchronization primitive that can let more than one thing into the critical section at a time. It's not so much for saying 3 threads can be in the bathroom, as much as it is to say there are 3 resources available, so 3 threads can take one of those resources. So semaphores are usually used to keep track of resources. We can also use semaphores in a method that makes them behave like locks, and we can use them to get behavior like thread join by using them as a barrier semaphore. Then we have condition variables, which we find ourselves inside of a critical section protected by a lock, but we can't proceed because whatever condition we need to be true is not true, and the only way to make it true is if we give up the lock. So a condition variable lets us safely wait inside of a critical section until the condition is changed, and we might be able to proceed. All right. Now, before we get going any further, I just want to issue a little word of warning. If you hear a very loud thump that sounds like somebody banging into something, I have I think it's a mountain ash tree in my front yard. It's full of these little orange berries. And there is a very large flock of cedar waxwings, which is a funny little bird. And they're back today. They were here yesterday. And every probably 10 minutes, they fly into my window. So if you hear a bang, it's just a bird flying into the window, and the bird is probably fine. And if it's not fine, I'm sure the neighborhood cats will have a good feast tonight. All right, now, what we have is we ended last class introducing you to a particular sample problem. One of my pet peeves of Mac is the dock. If you use a dual screen window, the dock will shift to whichever window you are. It perceives you are using, and it's often wrong. So at the end of last class, we introduced this problem here called Sem2CV. So if you're on Piazza, you can open up Sem2CV in the handouts, and you'll see we have this little bit of code, and it's using 3 semaphores for the synchronization. And what the question is asking you to do is to rewrite this code, but instead of using semaphores, we'd like you to use locks and condition variables. Now, as it turns out, there is more than one solution here. Not all solutions are going to give you the same synchronized behavior. I'm going to show you one possible solution, and I'm going to leave it up to you to come up with other solutions on your own. So let's make that nice and small. Let's get up a nice little here. Okay. Now I like to use lines because that way I can actually draw nicely. Okay. So here we go. Let's actually solve this. So the first thing I'm going to do is I'm going to make the observation that semaphore A and semaphore B, their initial value is set to 1, which means they start with 1 resource. And then if I look in function 1 and I look in function 2, I note that semaphore A and semaphore B are both used as binary semaphores, which means they're locks. So let's just replace semaphore A and semaphore B with a lock. Now, because I have a third semaphore, I need to use a condition variable still, I probably am going to need another lock, so I'm going to create a lock C to start with. And now let's look at function 1's code. So function 1, we're just going to replace semaphores A And again, I'm using pseudocode here. There we go. So we've done the first part, but now we have to look at the second part of function 1. And what I see here is that function 1 has to wait for a resource on semaphore C to be available. Semaphore C starts out as 0 resources available, which means that function 1 is going to be consuming resources. And if you take a look at function 2, you'll see that function 2 is the one responsible for producing those resources. So really, I need to introduce a CV, and I'm going to call it CV out of total boredom. And I'm going to also introduce a counter, and the counter is going to keep track of how many resources are available. There we go. So what I'm going to do is I'm going to use lock C to protect the shared variable count. And what I'm going to do is I'm going to acquire lock C, and then I'm going to do some stuff with count, and we'll go from there. So we acquire lock C. Now I want to take a resource. So there's many different ways you can implement this. I'm going to show you a rather peculiar way of doing it. And then on Piazza, why don't you post your own solutions and I'll let you know if they work or not. So what we're going to do is we're going to preemptively decrement the counter. Now, what's interesting here is if the count is less than 0, then it meant that there were no resources available. And so count would be negative, which means that we shouldn't be able to leave this function until we've produced a resource. Think of it as you need to pay your tuition, which is insanely high. You don't have the money from your co-op yet because your co-op employer forgot to pay you. So the bank is going to let you overdraw your account, and at some point later we'll let you proceed once your co-op employer has actually paid you. So we're going to overdraft our account, and then we're going to wait. So if count is less than 0, now here's the thing. Because this shared variable is protected by lock C, if I try to wait here without releasing the lock, then nobody could acquire the lock and change the condition. So what I want to do instead is we're going to call CV wait. Like that. And when we wake up, we're going to make the assumption that the count is now greater than 0. Or we would be making the assumption that a resource has been produced for us, not that necessarily that the count has been greater than 0. Here's the problem. If you wait for the count to be greater than 0, what if 100 copies of function 1 come and they all decrement count at the same time? If you had to wait for count to be greater than 0 before you were woken, then the problem that would happen is you would have 100 people waiting for the producer to run 100 times. But they'd all have to wait the same amount of time. Why do we need to do that? Why don't we let the consumers go one by one as the producer produces each individual resource? So that's kind of the strategy we're going to use here. It's not to say you can't solve this with a while loop. It's just you need to be careful because you don't want all the consuming threads to have to wait until every resource has been produced to go. I mean, if you think about it this way, if you go to a bakery and the bake shelf has no cupcakes and 10 of your friends come in and they're sitting there waiting for cupcakes as well, do you all have to wait to purchase the cupcakes until there's enough to serve all of you? Or as the cupcakes come out, do you take them and leave the store? So we're going to do the latter there. Once you wake up, we release the lock because we're all done with it. All right, so there's function 1. So this is just a lock And all right. So let's look at function 2 then. I'm going to write it with a different color so we can differentiate them. At this point in time, I'm actually wishing I had a motorized head on my tripod, because if I did, I would turn it around and let you see like the 30 or 40 little birds that are sitting in front of my window feasting on berries. All right, so in function 2, we look at function B, and we see that it is protected by semaphore B, which was a lock. So we're just going to replace that semaphore with our lock B. So we're going to acquire B, then we're going to call func B, and then we are going to release B. There we go. Now we need to have the producer code that what we had before was calling V on semaphore C. And remember, when you V a semaphore, you're giving it a resource. It increments the count by 1 and then wakes up exactly one thread that may be waiting on the semaphore. So taking that into consideration, what we're going to do over here then is we are going to be changing the value of count. So we need to acquire lock C. Acquire C. And then what we're going to do is if the count is less than C, or less than 0, then I know for certain, I know that there is a thread there could be a thread, or there is a thread waiting for this. Because if the count is equal to 0, then either no threads have entered or there's no threads waiting. And if the count is greater than 1, then how could any threads be waiting? So if the count is less than 0, I'm going to call CV signal. Now, does it hurt to call signal even if there's no threads waiting? Actually, no, it doesn't. Is it a few extra pieces of code that would increase the length of time? Yes, but not by any noticeable amount. All right. So now that we've woken up the thread won't run. Because remember, when you are woken, you don't go from blocked to running. You're going to go from blocked to ready. And even if let's say there was a context switch here and you went from ready to running, inside of CV wait, you would be trying to reacquire the lock. But since function 2 still has it, function 1 is going to have to wait for us to relinquish the lock to them. And before we relinquish the lock, we are going to increment the counter to indicate there's another resource available. And then we are going to release our lock. So there you go. There is one possible solution for this. There are many, many others. And I would encourage you to try this problem and post your solutions to Piazza. Just make it a single thread where you can everybody post. And I'll let you know if you're on the right track or if there's any particular problem with it. All right. So that concludes our talk of condition variables and semaphores. We ended off talking before about how to do producers and consumers. And if we go to the very next slide, you'll note that we are changing topic. And so the next thing that we actually need to talk about here is this concept of race conditions that arise from not your code, but race conditions arising from things like the compiler and the CPU. All right. Now, you may have noticed, and I know a few people have actually made some comments on Piazza about how volatile is used all over the place. And we haven't explained to you exactly what volatile is and why it's so important to use it. And I'm sure if you went on the internet, you'll find there's a lot of arguments and discussions about whether or not volatile is actually relevant. A lot of people are wrong. But we're going to talk about what volatile is today. So first off, one of the things I want to mention is that there are actually 3 sources that race conditions can come from. The biggest source of race conditions is actually you. You've written some code that's multi-threaded, and you haven't thought too far ahead about how many threads could be reading and writing certain shared variables at the same time. So the primary source is you. But your compiler and your CPU can both introduce race conditions. Now, this is not something that typically arises in OS 161 because we're using a very old CPU that's simulated, and our compiler is also very old. Now, how do race conditions arise from these 2 things? Well, this is not your fault. The reason why race conditions arise from both the compiler and the CPU is because they are trying to optimize the code that you have. The compiler, of course, is trying to figure out what is the smallest and most efficient set of assembly instructions we can use to do the tasks that you have asked it to do. So the compiler is going to reorder instructions and try to eliminate things as best as possible. I'll go into a greater detail about Volatile's particular compiler optimization in a minute. Now, what takes everybody by surprise is that the CPU does the same thing. The CPU has the ability to look ahead at what instructions are coming down the pipeline, and then it has the ability to say, you know, it would be faster for me if I just reordered these 2 loads and stores. And if I did it that way, then maybe we don't need these knobs, or maybe my pipeline would finish faster. So both your compiler and your CPU are reordering instructions in order to give you faster running code. The problem, of course, is that your CPU and your compiler don't know that your code is multi-threaded, and so they can introduce race conditions by changing the order of assembly. Now, what you'll see with most modern languages and most modern architectures is that they are giving you what's known as a memory model. And what a memory model is it's some instructions about how threads are going to access memory in any shared region. So it's telling the compiler and the CPU which optimizations are permitted to be performed and in what order during blocks of code which are shared. Now, we don't have a memory model for our old version of C or for the R3000, so don't worry too much about this. We do, however, have to worry about volatile. So our compiler, although it is old, still is capable of performing some optimizations on our code. One of the most common optimizations you'll see these days is the desire to keep the value of a variable stored in a register instead of keeping the up-to-date value stored in memory. Now, why would we want to do that? Well, that should be fairly obvious. Here's the problem. If every time you have to access a variable's value, you would have to load the address of where that variable is stored, then you have to load the value from memory, use it, and then store it back to RAM. So you are looking at a minimum of 3 memory operations. Remember that loads and stores take more cycles than anything else. So 3 loads and store operations just to add one to a variable. That's a lot of work. If I instead keep the up-to-date value of the register of the variable in a register, I don't have to load it. I don't have to store it. I just keep it there. And then when I'm finally done with that variable's value, I can just store it once back to memory. So if you look at the sample code on this slide, you've got a shared global variable called shared total. And then you've got function A and function B that are both going to use shared total. Now keep in mind that the compiler doesn't know that function A and function B could run at the same time. And so when the compiler is assigning registers to variables, it may assign register 3 for shared total in function A. And so for the entire body of function A, the up-to-date value of shared total is stored in register 3 and not in memory. And then in function B, the up-to-date value of shared total is going to be stored in register 8. Now what happens if function A and function B are running at the same time? Does register 3 have the correct value of shared total, or does register 8 have the correct value of shared total? And the answer is probably neither of them. And memory isn't correct either. So this is an optimization that most compilers do. It's a huge problem for multi-threaded code. So what we can do to get rid of this particular optimization is we can tell the compiler to disable it. Now, you don't tell it to disable it for like the file or the program. We tell it to disable this register allocation optimization for the shared variable. So if we simply indicate that shared total is volatile, then that register allocation optimization will be disabled, which means that every time we try to access shared total, we will have to load it from memory and then store it back to memory afterwards, every single time. So it's not going to be as efficient, but we won't end up with this particular race condition. Now, some people are under the mindset that volatile is going to get rid of race conditions, all race conditions with respect to a shared variable. And that's simply not the case. Volatile does not equate to a lock. Volatile is disabling a compiler optimization. That is all it does. You should make sure that any shared variables you have in your lock or your CV implementations or any shared memory that could be accessed by multiple threads, it's important that you make it volatile. And it doesn't matter if you put the volatile keyword before or after int. Both are perfectly acceptable. Now, our ancient version of C doesn't provide us with much other than that. Volatile will disable the optimization, and volatile does one other thing. So if you declare a bunch of assembly code volatile, it will also make sure that when the compiler is doing optimizations for reordering, that region of code does not get reordered. And that's actually really, really important, because if you reorder instructions, you're going to possibly have two things accessing the same memory at the same time, and we don't want that to happen. Modern languages, in addition to volatile, modern C and C++, are going to offer things like the memory model. And they do that by giving you a bunch of built-in language-level synchronization functions. So these functions are things like locks and so on that the compiler is aware of. So if you use the language-level synchronization function, then when the compiler is compiling that code, the compiler will be like, oh, I see this magical function here. I know that this is the start of a multi-threaded piece of code. And so when the compiler sees that language-level function, it won't perform any optimizations that would cause race conditions. And effectively what it means is the order of instructions that it will produce for that protected block of code will be exactly the order that you have listed them in. So it's not going to reorder them for any purpose whatsoever. So that's kind of neat, right? All right. Now, again, OS 161's version of C doesn't support this. But certainly C++ 11, the latest C version, Java, any modern language would have these language-level synchronization functions or blocks to actually protect for multi-threaded code. And it's something that if you're out there looking for something to do because you're so bored, I would definitely take a look at it and get some experience with it. Somebody wants to write volatile int volatile. I don't know if that works. It's one of those things, a lot of people ask me, like, does this very strange piece of code work? And it's written all weird. And I'll be like, I don't know. I am not a walking C-spec. That's my husband. And if it's a weird piece of code, why would I have typed that to try it? If you're curious if it's going to work, open up a C compiler and try it and see what happens. I know it's a joke, okay? Still, it's one of those things where somebody might try it and I don't know what's going to happen. All right. Now, in addition to the compiler offering us these language-level synchronization functions to make the compiler aware of regions of code where multiple threads could be running at the same time, What we also find is that the CPU, because it also has a memory model which dictates how threads are going to access shared memory through a shared piece of code, the CPU also provides its own functions. Now, CPU doesn't provide functions. CPU provides instructions. And these instructions, they're going to be assembly instructions that are like barriers or fences, kind of like load, link, and store conditional. And but there's others as well. And what these instructions are going to do is they're going to say, okay, when I enable this fence, I'm telling the CPU, do not reorder anything until the fence is closed. So the CPU will simply execute the instructions exactly as it reads them without doing any reordering whatsoever, so that memory reads and writes happen exactly according to the memory model. And then, of course, you have to make sure that if you're putting the barrier in place, make sure you remove the barrier when you're done accessing that shared bit of code. And again, the MIPS R3000 that we are using is both old and simulated, and it doesn't have this, so you don't need to worry about it so much. All right. So those are the other two sources of race conditions. Now, a common question, by the way, I like to ask, and I know you don't have a midterm, but it might show up on like a true-false or a multiple choice thing. You never know on Learn. I like to ask, what are the sources of race conditions? Remember, there are three sources. You, being that you have code that you have written where you have multiple threads reading and writing a shared variable at the same time. The second source is the compiler's optimizations, and the third source is the CPU's optimization. So those are the three sources. All right. Now we have some other topics to kind of tidy up. So when we gave you multiple threads, we gave you the ability to do better CPU and resource utilization. You have the ability to have higher performance code because, of course, if you have multiple CPUs, all of them can be running code in parallel. And then we realized that that's going to give you the problem of multiple threads reading and writing a shared variable at the same time. And so we have these race conditions. So we give you locks and semaphores and condition variables and many, many other tools to help you eliminate the race conditions. And you might be thinking, okay, I've got these tools, I'm off the hook, we're ready to go. And the answer is simply no, you're not. Because you have to be able to use those tools properly. If you use synchronization primitives improperly, and this is on you completely, you could end up with not solving the race condition, or you could end up with another really bad problem known as deadlock. So if you look at this following piece of code here, what you've got is lock A and lock B, and two functions that could run in parallel. So function A is going to acquire lock A followed by lock B. And function B is going to acquire lock B followed by lock A. Now that probably doesn't seem like a big problem. It's a huge problem. Because what can happen is, let's suppose function A acquires lock A and then there's a context switch. Actually, we can draw this. Let me find my little tool. We'll go here and we'll do a window snapshot. Let's grab that. So what I'm doing is I actually want to draw on this slide here. And we can sort of do that. There we go. Maybe my pen. So let's say that we have function A acquires this. So that happens first. And then there's a context switch. And then let's say that function B, it then acquires lock B. And then there's a context switch again. And now Third thing that happens is function A tries to acquire lock B. Now, lock B is owned by function B, which means that there's going to be a context switch here. Thread A running function A is going to go to sleep, and the context switch goes back over here, where we try to, as the fourth operation, we try to acquire lock A in function B, except, of course, function A owns lock A at this point. So what's going to happen is that function B's thread falls asleep, and who wakes them up? Nobody. Nobody can wake them up, because remember, with a lock, the only person who can release it is the person who owns it. And the thread that owns lock A is asleep waiting for lock B. And the thread that owns lock B is asleep waiting for lock A, which means these two threads are asleep forever. Forever. Nobody can wake them up. Nobody. We call this situation deadlock. Now, there's also another situation called live lock. And what live lock is, it's kind of a situation where, let's say you're spinning, you're constantly trying to do something, and you're rechecking, and the condition never becomes true. You're still alive, you're still executing instructions, but you never actually make any progress. So live lock is another thing, but we don't really talk about it much. We're more concerned about deadlock. Okay, how do you solve this problem? So, first off, if you're looking for your compiler or the operating system to help you out here, they can't, and they're not going to, because they don't know if that was intended or not. How could they know if that was intended? Now, I get a lot of people say, well, couldn't the operating system note that this thread has been asleep for so long? Why don't we wake it back up and get it to run again? Okay. But how does the OS know it's safe to wake the thread up? What if the thread is genuinely waiting for something? And that something will eventually genuinely become available. How would the OS know that? So it doesn't really make sense to have the OS interfere here. So, as I said, these two threads are deadlocked. That's what it says on the next slide. We're going to need you, the user, to do something to solve this problem. Now, there is a method which involves the OS a little bit called the banker's algorithm. We're not going to go over that here, which is involved with, keeping track of how many resources each thread has, and then you can only acquire a resource if there is enough system resources available in order for you to perform your transaction. We're not going to go over that complicated algorithm. But there's three very simple strategies that you can use to prevent deadlocks in your code, and it's on you to do this. So the first one, which is not on the slide, I'm going to switch over to OneNote actually here. So let's do a new page, and let's get some nice lines up here. There we go. So the first thing that we should do, or make this option 1 for deadlock prevention, don't acquire a lock you already own. That kind of makes sense, and when we talked about our lock implementation, we already discussed that. If you try to acquire a lock you already own, you're going to fall asleep and nobody can wake you up. So it makes good sense to assert that you don't already own the lock. Now, you might be wondering, why don't I just return from lock acquire right away if I own the lock already? That's called letting your programmer away with murder. You're letting them acquire a lock multiple times that they already own, which is something they should never do. So in my opinion, this is one of those cases where you should kill the program to be the slap in the face that says, hey, don't do that. That's bad. That's my take on it anyways. So that's the first step. The second thing you can do is no, hold, and wait. Now, no, hold, and wait is interesting. What it says is that you may not own any resource while you are waiting to acquire another. And what they mean by wait doesn't mean sleep. It means sleep or spin. So while you are sleeping, waiting to acquire something, or while you are spinning, waiting to acquire something, you may not own anything. In order to implement no, hold, and wait, you actually need a special version of a lock. So you need a function called try acquire. This is not in your notes, by the way. And what try acquire is going to do, of course, this is pseudocode, so all of the appropriate K assertions will go there. And then what we're going to do is we are going to acquire the spin lock, because we're going to check if the lock is available. And then we're going to say if the lock is held, try acquire is not going to then call acquire and have this thread be put to sleep. What try acquire is going to do is if the lock is not available, instead of going asleep, we're going to return false. Lock not taken. So we are going to release our spin lock. And then we are going to return false. What about if the lock is available? So if the lock is available, that's where we are down here now. So the lock is available. Then we're going to set, since we own the spin lock, or we don't, nobody owns the spin lock. Sorry, confusing. We own the spin lock, and the lock is not available, so we can now take the lock. And we'll set the lock owner is going to be curthread. By the way, you'll notice that I have held and owner, and I'm going to tell you that there's a sneaky little trick you can do such that you actually only need one of those variables, and I'm not going to tell you what the trick is, but I'm sure you can figure it out. And then we're going to release the spin lock, and since this time we got the lock, we return true. There you go. So if you have this special try acquire function, we can now do no, hold, and wait. So let's do an example. Let's suppose that we had the code from the slides where we've got lock A and lock B. So this is what we're going to do in our function. So in function A, scroll some more here. I'm going to acquire the first lock. Now you'll note I'm not using try acquire here. There's no need to use try acquire because at this point in the shared block of code, I don't own any resources. I'm allowed to wait if I own nothing. So I acquire A, and now I need to try to acquire B. So while I am not able to acquire B, this is going to be very strange what I'm about to do here. I'm going to release A because I am not allowed to own anything while I'm waiting. And waiting means sleeping or spinning. So I release A, and then I'm going to acquire A and try again. Now you'll note I put some space here because to encourage other threads to run instead of just executing this loop a few more times, we can probably improve our performance a little bit if we just put a yield here. So there we go. So if both function A and function B were to do this code here, then when we reach this line here, we would own A and B. And it would be perfectly safe. That is, there would be no deadlock. Now, this doesn't seem too bad, right? But what if I had 3 variables? Let's say instead of 2 locks, now I've got A, B, and C. Well, then I'm going to acquire A, and it really starts short forming now. And then I've got while I can't try B. I'm going to release A and then try acquiring B. And then, this is where it gets real fun. Well, then we have to ask ourselves, well, what about C? So at this point, I have A and B, but now I need to try C. So while not B here, but C, I have to release A, I have to release B, and then I have to try to get A and B all over again. So then we do go to 1. Sorry, that shouldn't be B there. That should be A. So no hold and wait can work, but as you can see, it's quite a burden on the programmer because number 1, they have to implement try acquire, and number 2, you've got to sequentially make sure, okay, well, I've got A, now I'm going to try to get B. Okay, now I've got A and B, now I'm going to try to get C. And if I can't get C, I have to release A and B and start the whole process all over again. So it's some really nasty spinning where you can't own anything while you're repeatedly trying to get the same 3 things over and over again. So that's one option for your code to prevent against deadlock. There's an easier way. So option 3 is called resource ordering. What resource ordering says is that we are going to assign every resource in the system a unique number. And then we are only allowed to acquire resources in a strictly increasing order. So we don't need any special lock functions. The only thing we need is to assign numbers to our resources. So in our case from before, we had 2 locks, A and B. And just for simplicity's sake, we're going to say A is 1 and B is resource 2. So then inside function A, we would simply acquire A, and then acquire B. And we're not going to worry about the release. The release doesn't matter so much. And then in function B, well, inside of function B, we always must acquire in a strictly increasing order, which means we also in function B have to acquire these as A, B. And because we've done it in this way, we don't get deadlock. Because what's going to happen is, let's say we acquire A, and then there's a context switch. Well, then we try to acquire A in the other function, but then we're going to go to sleep. Which means that we come back here, and then as our third step, we acquire B in function A, and then that happens successfully, presumably if there's only these 2 threads. And then we're going to proceed into our critical section, and then we will release B. and then we release A. And when we release A, then we can come back and this can acquire A, and it just works out. Now that sounds really simple, and you might be like, oh, why would you ever use no hold and wait? Because in this case, resource ordering looks simple because we only had 2 resources. What if now instead of 2 resources, I had n resources? But what if these resources were given to me as just an arbitrary list, that is an unsorted list? If you have an unsorted list of resources, then you have to sort first. So if I have parameters, let's say I have A, B, and C, well, just because they're given as A, B, C as params, that does not mean they are sorted. So that means I'm going to have to sort these arguments first and then acquire them in order. And as you know, if we're doing any kind of comparison-based sort, the best you can hope to do, of course, is that there. So it's not that resource ordering is always better. It certainly has its complications. All right. Now, again, it is on you to make sure that you do this. It is not on the compiler or the operating system to figure out that you have deadlock or to solve it for you. And as I mentioned earlier in this section, it's actually Google did some analysis of the Linux kernel, and I think they found over 300 race conditions and deadlocks in the Linux kernel. Which aren't solved, which are actually still there. And I'm sure if they performed a similar analysis on Mac OS X or Microsoft Windows, I'm sure they would find just as many, if not more. So, something to think about. So we have a question here on Twitter that asks, why does it matter if the resources are sorted? Isn't it fine to use any arbitrary ordering as long as all uses are consistent? So the best way to ensure the ordering works out for resource ordering is to always acquire in a strictly increasing or strictly decreasing order. And every thread that is a part of that program has to adhere to that same ordering. So it's easiest to make sure, especially for a program that you have multiple people working on, it's easiest to choose one of those simple orderings at the beginning and say everybody must acquire resources in a strictly increasing manner. That actually brings up one of the interesting problems with resource ordering is you get a new developer come in, and supposing they went to U of T, maybe they were taught that you should acquire resources in a strictly decreasing order, and we teach a strictly increasing order. And so they go about acquiring resources in a decreasing order, whereas the rest of the code is increasing. Well, then you get a problem with deadlock, and nobody really realizes what's happened. So we like to keep to really simple, strict orderings for everything in the entire program. And of course, if you have multiple parameters, you could also just make sure that the parameters are sent in pre-sorted, but that really comes down to, do you trust your developers and your users to do the things they're supposed to do? So you do need to check to make sure that the arguments have been pushed in a sorted resource order. So, sorry, just reading the Twitch comments here. So the problem with acquiring a parameter 0's resource and then acquiring parameter 1's resource after that is, let's say that parameter 0's resource number is 7 and parameter 1's resource number is 3. If you then did that, and for the first thread had those parameters that way, so you would acquire 7 and then you acquire 3. And let's say the second thread has parameter 0's resource number as 3 and parameter 1's resource as 7. Then that other function would acquire them 3, 7, and you end up with deadlocks. So that's why it's really important to make sure that you are acquiring by resource number and not parameter number. Unless, of course, you can guarantee that the parameters have been sent in a pre-sorted resource order. It's just something to be careful with. All right, so with that, what I would like to do is show you one more sample problem. Now, we're not going to take it up today, but I just want to introduce it to you. We'll take it up next class or next episode. So this is the problem called QXfer. And what it is you have, I guess you can't see it there, so let's move that down. There we go. Again, this is in that sample problem bundle that's posted to Piazza. So you have n queues full of items, and we want to be able to transfer an item from one queue to another queue with multiple threads. So that is, we can have multiple transfers between queues happening at the same time. And what we'd like you to do is to figure out how to synchronize this using locks. So number one, how many locks do you need to perform the synchronization for this? And the challenge that I have for you is, what is the most number of threads that you can have running at any time without having a race condition or a deadlock? So we'll take a look at the answer to that another day. So what I'd like to do in these last little bit here before we go is I would like to talk a bit more about assignment 1, which is why I'm switching back over to OneNote here. Get rid of that. So hopefully you've all had an opportunity to actually get started on assignment 1. Certainly the solutions for lock and the solutions for CVs, we've already talked about how to do that quite a few times now. But we haven't really talked much about this traffic simulation problem. Actually, you know what? I'm going to get rid of the lines in this case because I want to draw. The grid probably would have made sense. Okay, so what you have in the traffic simulation problem is an intersection. And it's a 4-way intersection. And I'm going to apologize in advance. I don't have a driver's license. I've never had a driver's license. I have never opened the driver's handbook. I have no clue what the traffic laws are, and I don't care to know what they actually are. So if I'm saying some things that may seem funny with respect to real traffic, keep in mind that I don't know what real traffic laws are. And number 2, the traffic simulation problem on this assignment isn't a real traffic intersection either. So what you've got is you've got a 4-way intersection. My daughter knows this silly little rhyme that she goes around singing, "Never eat soggy waffles." And I never understood, why is she going around singing, "Never eat soggy waffles"? It's so weird. And then I realized, okay, yeah, it's the cardinal directions. But she, of course, she's 5. She doesn't realize that the rhyme she's been singing means the cardinal directions. It's still cute, though. All right, so we've got this 4-way intersection. And you can have cars go from north. You can also have cars come from south. You can have cars go east-west. You can have cars go west-east. And you can also have turns. So cars can go left. Yes, cars can turn left. And cars can turn right. And that happens for everything. So this is the permissible directions that people can travel in. So I'm going to have cars having accidents here. So that's what we're allowing, because cars can go in from any origin to any destination. And right now, if you look at the code, what you'll actually see is to prevent accidents from happening, there is a singular stoplight implemented as a semaphore that says 1 car is allowed in this intersection at a time. The problem, of course, is that cars are going to, let's make the cars all red, the cars are going to end up queuing and it's not fair. Everybody's going to have to wait a really long time, and so on and so forth. Now, here's the truth. Every term, there's usually one student who manages to get 80% on this problem without implementing a single line of code. We are aware that can happen because it's one of those things when you have multiple threads. It may just be that the order of execution at the time the TA runs your test worked out in their favor. So don't count on that, but be aware you may have heard that can happen. So what we want you to do, however, is we want you to change how this intersection synchronization is working to improve the flow of traffic. Now, we've given you a bunch of metrics to tell you how much time the total simulation should take based on how many threads and how many cars there are. We've given you numbers to say what's the maximum weight any car can have and what is the maximum average weight. So we've got a whole bunch of metrics to say what we want the performance of this intersection to look like when you're done. There's a few things I want to say. We have an epsilon. Okay? That means that we are saying that you have to be within that epsilon of the formula in order to get full marks. We're going to run your test multiple times. There are part marks available. I've reworked the marking scheme a few terms ago to make sure that it wasn't all or nothing, because it used to be all or nothing, and now there's part marks. So let's say that for one of the tests you pass fairness but not efficiency, then you'd get the fairness marks but not the efficiency marks, or not the full efficiency marks. So there is an epsilon, and there's also there are part marks available. So don't worry too much about that there. There are lots of different possible solutions to this. My recommendation to you is to throw away all conceptions of real traffic that you have. I know we give you the rules that indicate whether a collision is happening or not at the bottom of the page. I'm going to tell you some secrets about my implementation. Number one, my implementation is about 25 lines of code. Yes, it passes all the tests, all the time. Let me tell you some things about it. So number one, I never check the destination. So things that I do. I always see students' code that is very complicated because they've written a function to check whether a car is going to intersect, that has caused an accident with cars already in the intersection. Because a lot of people, the way they like to solve this particular problem is they create a matrix to keep, or some kind of vector or a list that keeps track of all of the cars that are actually in the intersection right now. And then when a new car tries to enter, they're going to ask, does this new car cause an accident with any of the cars in the intersection? So they have all this complicated code to check, is there an accident? And if there's no accident, they add it to the intersection and then they continue on. And that solution, what's nice about that solution is that's going to give you, I want to say, the most realistic traffic intersection, but it's not very efficient. I don't check if the cars collide. I don't look at the destination at all. I only look at the origin. It's all you need. I mean, maybe you have a better solution than I do, and that's totally fair. Synchronization problems are notorious for having multiple correct solutions. So I never look at the destination. I only look at the origin. I never, ever put a thread back to sleep after it has been waited. This is really important for decreasing max wait time. Well, let me explain what I mean by this. We often use condition variables in a while loop because when we wake back up, even though we were woke because the condition changed to what we needed it to be, there's still the possibility, because we don't go from blocked to running, there's a thread that may have run before us and may have changed the condition back to what we don't want it to be. So we usually use CVs in a while-up, usually. The problem here is that, let's say that you were trying to go from north to south, but that would have caused an accident. So you go to sleep, and then when the intersection clears, we realize, hey, you can go, so we wake you up. But let's say a car, and let's say you wake up and a bunch of other north-south cars go through, but then a car going east-west comes. And so when the previous car before you clears the intersection, and maybe there's an extra delay before you try to enter again, maybe the intersection clears and we switch the light, and then when you go to run again, you get blocked. So you go back to sleep again. There is this possibility for old threads to keep going back to sleep because you have no control over what order they're going to run in. And so that oldest car in the system wakes up, tries to enter, can't, goes back to sleep. Wakes up, tries to enter, goes back to sleep. And it just keeps going around and around and increases your max wait time. I do not have a while loop that checks the condition and puts the threads back to sleep. I do something called an explicit handoff, or what I call an explicit handoff. And what that means is that I'm going to make sure that when I wake a thread up, that is when the intersection clears, I am going to have the thread that performs the wake up change the light for me, thereby blocking anybody else from trying to enter and change the intersection on me, so that I know when I wake up, I'm guaranteed to be allowed to go through the intersection without causing an accident. And I'm not going to tell you how to do that, but it can be done. Now, my recommendation is to use condition variables. My recommendation is to also throw all your notions of real traffic out the window. Some things that I would also suggest is, how do you handle fairness? So here's the problem. Let's say the intersection is cleared and you've got to choose some cars to wake up. Well, you want to make sure that your max and average waiting times are minimized. So realistically, you want to wake up the older vehicles. And we don't want to use any timers to keep track of how long cars have been waiting for. Well, there's another way you can keep track of the oldest thing. You can use a stack. And you can use the stack to, or sorry, not a stack, a queue, to actually, no, the front of the queue is the oldest thing. So the direction or the cars that you wake are whatever is on the front of the queue. It's that simple. It's another way of keeping track of what is oldest, because we don't need to keep track of time. Now, I'm going to draw one quick thing here as a very quick hint. And I'm going to leave it at that. Now, I know you're probably wondering what all our tests are. I'm actually going to post for you some of our test numbers that we're going to use, so that you have a good idea as to whether or not your solution is going to work. If you don't get this working in time for the extended deadline, there's a couple things I want to say. Don't waste a slip day on it. It's not worth it, because assignment A2A and A2B and A3, you're going to want every last slip day you have available, or you may just want the bonus from the slip days. If you don't have the traffic problem working, it's not going to impact your other assignments at all, because honestly, what kind of operating system has a traffic light in its kernel? Maybe as an Easter egg. So don't worry too much if you don't have a perfect solution for this. All right, then. Just a couple things before we go. So do make sure that you get started on the traffic problem. Do note that there is an extended deadline for assignment 1. Do note that you should not be using slip days on assignment 1. It's not to say you can't, it's just that you should conserve them for the other assignments. And if you go on Reddit and talk to people there, they will suggest the same thing, because while the next assignments aren't terribly difficult to implement, they're an absolute bloody nightmare to debug. So you're going to spend like a day or two implementing and the next 3 weeks debugging them. So save your slip days for those. And the last thing that, sorry, comment on Twitter, you mean Windows doesn't run on digital cars running through a digital intersection? I mean, I don't know. Anyone want to call Bill Gates up and ask him? All right, so do get a start on A1 if you haven't already. The next thing I want to mention is make sure that you tune in to our next episode on Thursday, because we have something extra special planned that is going to be unique to the online offering of this course. So tune in next week for something special, very, very special. And I will see you all on Thursday.
Introducing Macintosh. It does all the things you'd expect a business computer to do. It does a lot of things you wouldn't expect a business computer to do. And it does some things no other business computer has ever done before. Of course, to do all this, you will have to learn to do this. Macintosh, the computer for the rest of us.
The development of Macintosh by Apple has been paralleled by the work of leading software developers.
It's a great machine. It's a step forward in terms of the way it uses graphics and the speed. And this is a machine that a lot of people are going to be able to afford. That's a very, very useful machine. I was enthused. Microsoft doesn't work with new hardware very often, but we put a team of people on it from the beginning, and we're planning that over half of our retail sales next year will come from Macintosh software.
At the back of Macintosh, you'll find 2 built-in ports for connecting a printer, a modem, or to Apple Bus, Apple's own local area network, as well as a dedicated port for an external disk drive. The Image Writer printer from Apple is specially designed for Macintosh. By plugging a modem into your Macintosh, you can communicate by telephone with electronic databases and news services. You can also emulate DEC VT100 and IBM 3278 terminals. You can expand the storage capacity of your Macintosh with an external disk drive, just like the one we built in. And if you work with lots of numbers, you'll appreciate the optional numeric keypad. And when you're ready to travel, Macintosh can easily go along. The durable carrying case is strong and waterproof. Your Macintosh, keyboard, mouse, manuals, and software all fit neatly inside. Even fully loaded, the carrying case is light enough to go anywhere you go.
The real genius of Macintosh, the world's newest personal computer, isn't its 32-bit microprocessor or its Lisa technology, or that it captures the power of a mainframe on a board 10 by 10 inches, or even that it costs half as much as computers half as powerful. The real genius of Macintosh is that you don't have to be a genius to use it. Macintosh, the computer for the rest of us.